Okay, welcome back. So in this video, I'm going to discuss about linear equation and Bernoulli equation. Bernoulli equation is easy to look at. It's the first order differential equation. The left hand side is just a linear operator, and right hand side is y to the power n times a coefficient of which is a function of x. And if n equals 0 or n equals 1, then this equation is simply either a separable equation or a linear equation. So we can solve for we don't worry about it. So in Bernoulli form, we are interested in when n is not equal to 0 or not equal to 1. So the idea is to consider a u substitution. So here the form of u substitution is 1 minus n y to the power 1 minus n. And using this u substitution, you get a new differential equation in terms of x. So let's write it in the form. Okay, so this converted differential equation will be a linear differential equation. If you are lucky, it might be just directly a separable equation, but usually it will be a linear differential equation. And that you can solve by looking at the integrating factor. And here at this stage, it is a good idea not to memorize the integrating factor, but rather you look at how to find the integrating factor. The integrating factor should be found by looking at the linear term, So we want to construct a new differential equation, d mu dx equal to something where mu is the integrating factor, and that something is just the linear term. Okay, so then this will be an equation for integrating factor. So this will give you the integrating factor. So this first order differential equation d mu dx equals p mu is easy to solve. Mu is e to the power px dx. Once you have the integrating factor, you go back and multiply this equation, linear equation, by the integrating factor, and that is something fantastic, that on the left hand side you will just get a derivative of something, and that derivative of mu times u. So u is the solution, mu is the integrating factor, and that can be integrated directly. So you can find u, and once you find u, use the back substitution, u equals y to the power 1 minus n to get the solution y. Good. So I'm going to illustrate this method starting with linear equation. So the first thing you identify, what is this equation, right? So we can see that we don't call this is Bernoulli equation, but eventually this is a Bernoulli equation, because on the right hand side, y to the power n, and n is 0. So you can think here y to the power n and n is 0, which means this is already converted to the linear form. And in order to solve this linear equation, so let's just concentrate on solving linear equation. Assume that we don't know anything about the Bernoulli equation. So but carefully we have to identify that whether it is linear equation or not, and that's the important. If you make a mistake to identify or to look at or convert or write it down into the linear form, then there will be some problem. So since this is a linear equation, so we find the integrating factor. And again, I am not suggesting you to memorize the formula for integrating factor. Rather, the idea of getting the integrating factor is you want to find a mu. So mu, let's denote mu is the integrating factor. The variable mu, Greek letter mu, is the integrating factor. So d mu dx, first derivative of mu, is written by looking at the linear term of the differential equation. Okay, so this is a simple first order differential equation that can be solved by separation of variable. So if you separate the variable, so you get d mu by mu, and then consider integrating both sides with corresponding variable. So on the left hand side, if you integrate d mu over mu, you get ln of mu. On the right hand side, we just need little work, which is not too terrible. Excuse me. And this one is going to be easy to integrate. You get 2x plus ln of x. Of course, there is a constant of integration, but remember, when we look for integrating factor, we are not worried about the constant of integration, is because we are going to multiply the differential equation by the integrating factor. So considering a constant of integration in mu would be multiplying both sides of your differential equation with another constant, and that constant will get cancelled. So it is obvious to think that when you find the integrating factor, you don't look for the constant of integration. So you get mu equals e to the power 2x plus ln x. So you can rewrite e to the power ln x and e to the power 2x as a product. And obviously this is x e to the power 2x. Okay, good. So you get the integrating factor x e to the power 2x. Now go back and write down the differential equation multiplied by the integrating factor. Now the point is that in this exercise, is a little work looks like on the left hand side, but keep in mind the idea of integrating factor is after you multiply the left hand side, then you should get a product rule on the left hand side, meaning that the left hand side should be in the form of x e to the power 2x times y, and now on the right hand side e to the power x and e to the power minus x get cancelled, and that would perhaps be little work to verify, but in most case it is obvious, and you can see here is that x e to the power x is the first function. You can differentiate y to get dy dx, and then you keep y, and then you have to differentiate x e to the power x to get this quantity times this quantity. So I leave that as an exercise and continue here by integrating this quantity. So you get integration of x and then a constant of integration. So on the right hand side, integration of x is half of x squared plus c, y equals, so you isolate y, so you divide by x e to the power x, so half x e to the power minus 2x plus c divided by x times e to the power minus 2x, and that's your explicit solution. Okay, so let's take a second example. And again, this is a first linear differential equation, and this time we are going to consider a condition. So it is a linear differential equation but not written in the standard form. So we first convert into the standard form. Right. So in order to convert into the standard form, you divide by the coefficient of the highest derivative, which is in this case x square plus 1. Okay. So because it is a linear first order differential equation, we look for integrating factor. Okay, and solve this separable equation. Excuse me. I solve this separable equation, and uh, so integrate it in the left hand side, ln of mu, in the right hand side. You need a little substitution to solve this equation, solve this integral. So let's say z equals x square plus 1, then dz would be 2x dx. And if you look at here, we have 4x, so we take 2 outside the integral, so we have 2x inside the integral, so 2x dx is dz, and x square plus 1 is z. So 2 ln of z, and you substitute that, and here ln operates on absolute value, so x square plus 1 is an absolute value, and we are not worried about the integrating factor. And left hand side you have ln of mu, on the right hand side you can write a ln of x square plus 1 to the power 2, hence the integrating factor mu is x square plus 1 square. Okay, so now what I'm going to do is I'm going to take this original equation, and then I'm going to multiply both sides by x square plus 1 square, and equals x times x square plus 1. So x square plus 1 get cancelled on the right hand side, and if you look at this one, the derivative actually will be coming from 2 x square plus 1 times 2x, so 4x times x square plus 1. So it is coming from d mu dx equal to something p of x times mu. Okay, so the right hand side would be p of x times mu. Nevertheless, so we have this, and we can see that this part is the derivative of this quantity, So we can rewrite x square plus 1 y equals x cubed plus x. And you actually don't have to do this calculation always. Once you multiply by the integrating factor, you should get ddx uh, integrating factor times y equals the right hand side, and right hand side you calculate by multiplying with the integrating factor. But how about if you make a mistake in your integrating factor calculation here, then that will be wrong. So it is a good idea to check here to confirm that you are good at this stage in your calculation. So now you integrate it, x square plus 1 square y equals 1/4 x to the power 4 half x square plus a constant. And maybe now it is a good time to find the constant of integration by using this condition here. Y of 2 is 1. So y at 2 is 1, y is 1, x is 2, so it is 2 squared is 4 plus 1 is 5, 25, 1/4, x is 2, 16, 4 plus c. So this one is 4 plus 2 is 6, 25 minus 6 is 9, so 19. So c is 19, and we can actually write down explicitly in form of y. Sorry, 19. Okay. So with this example, after doing this two example on linear equation, now I'm going to provide an example on Bernoulli equation. And I'm also going to consider a condition so that I can determine the constant of integration. And this is a first order differential equation, so I need only one condition. And remember, with this condition, it is called an initial value problem. So often you are asked to solve the initial value problem. So look at this equation. This part is linear. P is 1 by 2x, and this part is non-linear, which is in the Bernoulli form, y to the power minus 3. So n is minus 3. So this is in the Bernoulli form with n is minus 3. So we considered Bernoulli substitution. So u is y to the power 4, or you can rewrite y is u to the power 1/4. Okay. So now what you are going to do is looking at the substitution, and then you're going to replace y and dy dx in the original equation. So you need to calculate dy dx. So I'm going to calculate dy dx by first calculating du dx. So you can calculate by looking at u equals y to the power 4. Calculate dy dx, or by looking at y equals u to the power 1/4, calculate dy dx. It doesn't matter. So that should be 4 y to the power 3 dy dx. And we can see that y is u to the power 1/4. So we can rewrite this 4 y to the power 3/4 dy dx. Dy dx, you can put dy dx on the left hand side. Sorry, this should be a u. Okay, so you could have looked at here. Y is u to the power 1/4, dy dx is 1/4 u to the power minus 3/4 du dx. It's the same process in both directions. So you get dy dx plus y by 2x equals x by y cubed. So all you have to do, substitute. So 1/4 u to the minus 3/4 du dx. So y is u to the power 1/4, and here divided by 2x. Now maybe I can write down this one as x y to the power negative 3, and y to the power negative 3, y is u to the power 1/4, y to the power negative 3 will be negative 3/4, u to the power negative 3/4 on the right hand side. Okay, good. So okay, good. So now we have this Bernoulli equation in just in the form of a linear differential equation, for which you can find an indicating factor, and the equation for indicating factor you can look at the mu dx equals 2/x mu, and this simple equation we just now know that it is mu equals e to the power 2 by x dx, and e to the power ln of x, which means that is a 2, so which means x squared. So mu is just x squared. So you multiply the equation by d mu dx du dx plus 2/x u equals 4x. So you multiply both sides by x squared, and now you are lucky to get this form: x squared times u equals 4x, and then you have the integration. So if you integrate it, x squared u equals integral of 4x dx, which will be you have multiplied, so that should be here x cubed. So 4x cubed dx, and if you integrate, you get x to the power 4 plus c. So replace u with your change of variable, which is y4. So x4 plus c. So at this time you are perhaps in a situation to find the constant of integration by looking at y1 equals 2, which is a condition. So x equals 1 square, y equals 2 to the power 4, 1 to the power 4 plus c. So 2 to the power 4 is 16, and 16 minus 1 is 15. Hence x square y to the power 4 is x to the power 4 plus 15, and you can leave it like this because it's y to the power 4, so you are not going to find the the explicit form, which is more complicated. Okay, so good. Next example here. So I'm going to do another example, and this is all the examples I'm following the same procedure with a slight change in the calculation process. So everything should be okay. So for this example, I have a condition y at 1 equals 4. So this equation is not in the standard form. So first I'm going to convert this equation into the standard form without looking at it Bernoulli or linear. So in a standard form I am dividing by x. So I have x to the power half and y to the power 3 by 2. And in the standard form, I see that this is a Bernoulli equation with n equal to 3 over 2. Hence, I use the Bernoulli substitution y1 minus n, or y equals 1 minus 3 over 2, which is going to be 1 minus 3 over 2 is negative half. So y will be 1 by, you have to make reciprocal 1 by u, but then you have to power, so u to the power negative 2, and dy dx will be negative 2 u to the power negative 3 du dx. Okay, so now you have you have du dx. You can go back to the differential equation and convert the differential equation in terms of u. So on the left hand side, the first term is negative 2 u to the power negative 3 du dx for dy dx plus 1 by x u. Okay, u is u to the power, y is u to the power negative 2. On the right hand side, x to the power half, and you have y to the power 3 over 2. Well, y is u to the power negative 2, so y to the power 3 over 2 can be calculated from here. Y to the power 3 over 2, negative 2 times 3 over 2, so negative 3. Okay, now you convert the equation into the standard form by dividing by negative 2 u to the power negative 3, so you get a negative sign 1 over 2x, and when you divide u to the negative 2 by u to the negative 3, you get u. Negative half x to the power half and u to the power negative 3 get cancelled, and that is what we expect. On the right hand side there should be no dependent variable. Okay, so this is a linear differential equation, and we can find its integrating factor d mu dx equals by writing the second term on the left hand side, and as I'm following, I'm recommending you, and I follow that. I don't want to memorize the formula, so this is a separable equation, and I can also write straightforward solution. Feels like I'm memorizing the formula. So say it is not necessary to show your work if you can do that, but we don't lose. In fact, we gain. We lose the chance of making mistake if we show the steps. So ln of mu is going to be minus half minus half ln of x, so which is ln of x to the power minus half. So mu is going to be x to the power negative half. Now I will multiply the equation with x to the power negative half. The equation is du dx minus u divided by 2x equals negative half x to the power half. So after multiplication, minus half x to the power, it looks like minus 3 over 2 times u, and minus half and half cancelled, x to the power 0, which is 1, and then minus half. Okay, so this one you can easily see that this part is d dx of x to the power negative half. So that means you get d dx of x to the power negative half du dx, and on the right hand side just negative half. And this is something that you can just integrate it, right? X to the power negative half du dx equals negative half x plus a constant So you can find, wait a minute, I have a typo here. Sorry about that. So u, just u, and u is what? U is y to the power negative half. So x to the power negative half, y to the power negative half equals half x plus c. You can rewrite y to the power negative half equals negative half x to the power. So you're multiplying by x to the power half. So 3 over 2 plus c x to the power half. Now we're going to use the condition. Let's look at what is the condition given. Any condition? Okay, I perhaps didn't write down the condition here, so I'm going to know I have the condition here, right here. So y1 equals 4. So y1 equals 4. So 4 to the negative half minus half just 1 plus c. From here you get c equals so on the left hand side it is just half, and on the right hand side negative half. You take it to the left hand side, you get 1. Therefore you have y to the negative half equals negative half x to the 3 over 2 plus x to the 1 over 2. So that's a solution, but we can simplify that to write in terms of explicit solution. So what I'm going to do is I'm going to square both sides. So I get minus 1 on the left hand side, y to the minus 1, and if I square them together, so 1 quarter x cube plus x minus 2ab a plus b whole square. So x to the power 3 plus 1 is 4, so x square. Okay, so y equals, you just take the reciprocal and maybe you multiply by 4, so x cube minus 4x square plus 4. So that's your final solution. So I hope you enjoyed the demonstration. We have looked at Bernoulli equation, and the idea is you use a Bernoulli substitution to convert the Bernoulli equation into a linear first order differential equation. And to solve the linear first order differential equation, we get the integrating factor. So in order to illustrate that, I started with examples with linear equation, and then I moved to examples with Bernoulli equation. If you have any question, let me know. Thank you very much.